When a mathematical function is continuous, calculating the area underneath it is straightforward. But when a curve is highly fluctuating, the standard approach to measurement reaches its limit. The Riemann integral defines area by slicing the x-axis into narrow, contiguous intervals and constructing vertical rectangles that meet the curve. We see the formal definition here in Walter Rudin's Principles of Mathematical Analysis. Equations 1 and 2 define the upper and lower Riemann integrals. The process depends on finding the supremum, the lowest possible ceiling, and the infimum, the highest possible floor, for each vertical slice. This system fails if a function bounces between 0 and 1 infinitely often within a tiny horizontal interval. The upper rectangles stay at 1, and the lower rectangles stay at 0. Because they never converge, the area remains undefined. Riemann integration is structurally dependent on the function remaining relatively stable across contiguous sections of the domain. This dependency creates problems when dealing with sequences of functions, a series of curves that gradually converge into a final limit shape. In Chapter 7, Rudin highlights a technical crisis regarding these sequences. Equation 3 shows the expected behavior. The limit of a sequence of integrals should equal the integral of the limit function. In a complete system, we should be able to interchange these operations. Pointwise convergence reveals the fundamental flaw in the Riemann framework. A sequence of well-behaved integrable functions can converge into a limit function that is too chaotic for Riemann's rules to process. One side of the equation has a clear value, while the other side is mathematically undefined. This inconsistency makes the Riemann integral an incomplete tool for models in probability, for advanced functional analysis, and for theoretical physics, where swapping limits and integrals is a strict requirement. To resolve this crisis, mathematicians completely moved away from contiguous domain intervals toward a framework based on measure theory. The solution requires a conceptual pivot. We must move past the requirement of slicing the x-axis into adjacent intervals. Comparing the two methodologies side by side reveals the difference in strategy. Riemann looks at the domain and asks for the height of the function over a small section of the x-axis. Lebesgue looks at the range and asks, how large is the set of points in the domain where the function reaches exactly this height? Lebesgue's method groups non-adjacent points together based on their output value, ignoring how scattered they are on the x-axis. This requires a way to calculate the size or length of these highly scattered, non-contiguous sets of points on the domain. Partitioning the range is the core intuition of the Lebesgue integral, allowing us to process functions with infinite fluctuations. Executing this strategy requires the first building block of the theory, the measurable function. We analyze the function by selecting an interval of outputs on the y-axis. We trace this interval backward to see where it intersects the curve. When we drop these intersections to the x-axis, we identify the pre-image, the set of inputs that produced those specific outputs. A function is measurable if the pre-image of any open interval on the y-axis results in a measurable set on the x-axis. This rule ensures that no matter how the function behaves, the sets of points we project onto the domain will always have a well-defined mathematical length. Measurable functions act as the gatekeepers, restricting the theory to geometries that can be mathematically weighed. To calculate area, Lebesgue replaces Riemann's rectangles with simple functions. A simple function is a finite linear combination of indicator functions. The indicator function acts as a binary switch. It returns a 1 if an input is in a specific set, and a 0 if it is not. We multiply that switch by a constant, which assigns a specific height to that entire scattered set of points. The approximation theorem states that any non-negative measurable function can be precisely approximated from below by a sequence of these simple functions. We construct this by slicing the range into grids and filling the space under the curve with these simple functions. As we slice the y-axis into finer increments, the simple functions snap to the underside of the curve with increasing precision. The Lebesgue integral is the supremum of the integrals of all simple functions that bound the curve from below. By building the area using range-based simple functions, Lebesgue avoids the limitations of domain-based rectangles. We can now evaluate the Dirichlet function, which takes the value of 1 on rational numbers and 0 on irrational numbers. Under Lebesgue's rules, the Dirichlet function is a standard simple function taking only two values, 1, and 0. We group the domain into the set of rational numbers and the set of irrationals and multiply each by their height. Measure theory proves the measure of the rationals is exactly 0, and the measure of the irrationals is 1. The equation simplifies to 1 times 0 plus 0 times 1. The Lebesgue integral evaluates to 0, providing a definite value for a function that was previously unintegrable. Range partitioning handles these infinitely fractured domains, resolving the Riemann inconsistency with a single line of algebra. Because of this stability, theorems like the dominated convergence theorem allow mathematicians to safely interchange limits and integrals. This forms the foundation for advanced analysis, from LP spaces to the mathematical models used in quantum mechanics. Lebesgue saved integration by moving beyond the domain, redefining size with measurable sets, and building area from the range upward. This transition establishes the rigorous foundation for all modern mathematical analysis. Subscribe for more deep dives into these frameworks.